This content is produced by PassTheCSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable source-backed California materials so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. A roof can have soffit vents, ridge vents, and a clean inspection photo, yet still have a ventilation failure. The reason is simple. A vent is only an opening. Ventilation is a continuous route. I want you to picture three connected parts. Intake air enters low at the eaves. That air travels through an open channel beneath the roof sheathing. It leaves through exhaust vents high in the attic. If insulation, blocking, or a crush baffle closes the middle of that route, the vents at both ends cannot do the job shown on the plans. That is the central field decision in this lesson. I do not inspect vents as isolated products. I inspect the path from intake to exhaust. The most important point is the part that often disappears behind insulation and drywall, which is the clear roof framing airspace. Imagine a contractor who counts every soffit vent and confirms the ridge vent length, but never looks into the eave bays after insulation is installed. The insulation crew pushes bats hard against the roof deck. The exterior vents remain visible, but the intake path is choked. Moisture that reaches the attic has less opportunity to be carried away, and the upper exhaust may begin pulling air through ceiling leaks instead of through the intended eave openings. The immediate problem is not that the roof lacks vent products. The problem is that the air route has been broken. Based on the published Contractors State License Board study outline, roof framing is testable material. The useful contractor skill is recognizing that ventilation, insulation, framing, and moisture control must be coordinated before the work is concealed. The cited California residential rule starts with a baseline ventilation ratio of 1 to 150. That means the minimum net free ventilating area equals 1 square foot for every 150 square feet of the vented attic or enclosed rafter space. Net free area is not the rough hole cut into the building. It is the actual unobstructed area available for air to pass after louvers, screens, and other restrictions are considered. I use the listed net free area for the vent product rather than assuming the face size equals usable airflow. The chart puts the baseline and the reduced exception side by side. The baseline is 1 to 150. The reduced ratio is 1 to 300, but it is an exception with conditions, not the automatic modern standard. For the reduced ratio, 40% to 50% of the required ventilating area must be provided by upper ventilators located no more than 3 feet below the ridge or highest point. The balance must be placed low in the bottom 1/3 of the attic space, usually at the eaves or cornice. That high and low arrangement matters because the reduced total area depends on a properly distributed system. Here's a clean calculation. Suppose the vented attic area is 1,500 square feet. Under the baseline ratio, divide 1,500 by 150. The result is 10 square feet of required net-free ventilating area. If the project qualifies for the reduced ratio, divide by 300. The result is 5 square feet. That smaller number is not earned by merely installing a ridge vent. The upper and lower placement conditions still have to be satisfied. In climate zones 14 and 16, the source report identifies an additional vapor retarder condition for use of the reduced ratio. I would not generalize that detail across the state from memory. I would verify the climate zone, the approved assembly, and the current code requirements for the project. Vent opening dimensions also matter. The cited rule limits the least dimension of an opening to at least 1/16 of an inch, and no more than 1/4 of an inch. Larger architectural openings need compliant corrosion-resistant backing that preserves that protection. In wildfire-prone locations, I also verify the applicable California ember-resistant vent requirements rather than assuming an ordinary screened vent is acceptable. The ratio tells me how much net free area is required. It does not prove that air can travel through the framing. At an eave or cornice vent, the cited residential rule requires at least 1 inch of clear airspace between insulation and the roof sheathing. The key word is clear. The dimension applies to the actual unobstructed channel, not to the thickness printed on a baffle or the space that existed before a bat was compressed into it. The field checklist begins at the intake opening and follows the route upward. I confirm that bridging, blocking, and insulation do not stop the free flow of air. I confirm that the baffle is secured so it will not collapse when insulation is installed. I confirm that the 1 inch channel remains open beneath the sheathing at the vent location. Then I confirm that the route continues toward the upper exhaust. A baffle is a practical control, not a magic product. Its job is to hold insulation away from the deck and preserve the channel. It can also limit wind washing, where incoming air moves through or across insulation and reduces its thermal performance. But a baffle that is crushed, cut short, or buried behind blocking does not preserve the required path. This is where sequencing becomes contractor work instead of trade work. The framer establishes the bay. The vent installer creates the opening. Out, the insulation installer fills the thermal cavity. The person supervising the project has to verify that those separate scopes produce one continuous system. I make that check before concealment because correcting a blocked eave after drywall and finishes are complete turns a small coordination miss into invasive rework. The same principle applies in a vaulted ceiling where drywall follows the underside of rafters. Each enclosed rafter space needs its intended ventilation path unless the approved design uses a compliant unvented assembly. Stuffing insulation tightly against the deck and hoping the ridge vent handles the rest does not preserve an airway. Suppose a remodeling crew opens a cathedral ceiling and finds stained sheathing above bats that were packed against the roof deck. That finding does not prove a single cause by itself. Roof leaks, indoor moisture, air leakage, and blocked ventilation all require investigation, but the missing airspace is a supported defect condition, and I would not close the assembly until the intended moisture control path is identified and restored. Condensation is the reason the hidden air route matters. Warm interior air can carry water vapor upward through ceiling penetrations, attic hatches, recessed fixtures, and unsealed framing joints. When that vapor-laden air contacts a roof surface cold enough to reach the dew point, some of the vapor becomes liquid water on the sheathing or framing. One wet morning does not automatically mean structural failure. The concern is repeated or prolonged wetting. If the wood stays damp, moisture content can rise into a range that supports fungal decay, warping, and mold growth. Insulation can also lose performance when it becomes wet or when air moves through it. I keep two controls separate in my mind. Air sealing limits the amount of warm interior air and vapor entering through leaks. Ventilation gives moisture and heat in a vented attic a path out. One does not excuse poor execution of the other. The cause and effect chain is worth remembering. A ceiling leak path delivers warm, moist air. A cold roof deck brings that air to its dew point. Liquid water forms. A blocked eave channel slows drying and removal. Repeated exposure can damage sheathing, framing, insulation, and finishes. That is a realistic sequence, not a guarantee that every blocked vent produces rot. The memory connection is intake, airway, exhaust. Intake without an airway is only a hole. Exhaust without intake may pull from unintended leaks. The complete route is what makes the vented assembly work. An unvented attic uses a different strategy. I do not describe it as a vented attic with the vents forgotten. It is a separate moisture control assembly that moves the thermal boundary to the roof deck and keeps the attic within the building thermal envelope. The basic sited pathway uses air impermeable insulation applied in direct and continuous contact with the underside of the structural roof sheathing. Direct contact matters because the insulation and air control layer are intended to stop interior air from reaching a cold concealed surface behind the insulation. The decision matrix separates 4 reported strategies. The first is air impermeable insulation only, directly against the underside of the sheathing. The second is air permeable insulation only, which carries additional requirements rather than functioning as a simply sealed cavity. The third is a hybrid, with air impermeable insulation against the sheathing and air permeable insulation below it. The fourth uses sufficient continuous rigid insulation above the roof deck with air permeable insulation below. For the air permeable only pathway, the source report identifies a vapor diffusion port within 12 inches of the highest roof point, size at 1 to 600 of the ceiling area, with a membrane rated at 20 perms or greater. It also identifies a 2-inch airspace at the blocking and mechanical air supplied at 50 cubic feet per minute for each 1,000 square feet of attic area. Those details are assembly conditions, not optional accessories. For a hybrid assembly, the air impermeable layer stays directly against the sheathing, and the required thermal resistance of that layer depends on climate zone. For an above-deck, rigid insulation strategy, the continuous insulation must be sufficient to keep the monthly average temperature at the underside of the sheathing above 45 degrees Fahrenheit under the cited pathway. In climate zones 14 and 16, the report also identifies a Class 1 or Class 2 vapor retarder condition for certain unvented attics using air permeable insulation. That is exactly the kind of detail I verify against the energy documents, approved plans, and current California code rather than reducing it to a statewide slogan. The practical distinction is straightforward. A vented attic manages moisture through a designed air route. A compliant unvented attic manages moisture by controlling air, vapor, and temperature at the roof assembly. Mixing the two strategies casually can remove the protection each one depends on. Imagine a crew that omits soffit and ridge vents because spray foam is planned, but the foam is installed with gaps behind it and does not remain in direct contact with the deck. The project no longer matches the clean air impermeable pathway described in the report. I would stop concealment, document the condition, and obtain an approved correction rather than guessing that more insulation somewhere else solves the contact problem. Roof framing coordination also includes attic access. For combustible ceiling or roof construction, the cited residential rule requires an access opening when the attic exceeds 30 square feet and has a vertical height of 30 inches or more. The minimum rough framed opening is 22 inches by 30 inches. When the opening is in a ceiling, the report also identifies 30 inches of unobstructed headroom above the access point. If mechanical equipment is installed in the attic, the access must be large enough to remove the largest piece of that equipment, so the basic opening size may not be enough. I treat that as a planning issue before framing is locked in. The access location has to work with trusses, ceiling framing, ducts, electrical work, insulation, and the future service path. A minimum opening that cannot serve the installed equipment is not practical coordination. The work sequence changes the fall protection trigger, and mixing the numbers creates a real supervision error. During residential framing, when employees are walking or working on top plates, joists, rafters, trusses, or beams, the cited California Title 8 rule requires personal fall protection, guardrails, or safety nets when the fall distance is 15 feet or more above the lower level. During residential roofing operations on slopes up to and including 7 units of rise and 12 units of run, the cited trigger is 6 feet or greater. On slopes steeper than that, protection is required regardless of height under the source report. I remember the distinction by construction phase. Skeleton work is framing. Roof covering work is roofing. The activity controls which cited trigger applies. Attic entry adds a different safety decision. A competent person must evaluate the space before entry operations and determine whether it is a permit-required confined space. I do not assume that every attic needs a full permit program, and I do not assume that a small attic is automatically harmless. A permit-required condition can arise from a hazardous atmosphere, an engulfment hazard, or an internal shape that could trap an entrant. The report gives curing spray foam fumes as an example of a possible atmospheric hazard. If a severe condition is present, the contractor needs the required written program, monitoring, and rescue provisions before entry. If it is not present, the evaluation still matters because the classification must come from the actual conditions, not habit. Before I approve concealment, I make one final distinction. Is this roof assembly designed to breathe through intake, airspace, and exhaust, or is it designed as a compliant, unvented thermal enclosure? I do not accept a half-vented, half-sealed assembly without an approved basis. For a vented assembly, I verify the required net-free area, the distribution of upper and lower vents when the reduced ratio is used, the protected opening size, the 1-inch clear path at eaves, and the continuity of the channel pass insulation and blocking. For an unvented assembly, I verify the insulation type, direct contact where required, vapor and thermal controls, climate zone conditions, and the approved project details. I also verify that access is usable, that mechanical equipment can be removed, that fall protection matches the activity, and that a competent person has evaluated attic entry hazards. Those are separate checks, but they all meet at the same general B responsibility, which is coordinating work before hidden conditions become defects or safety problems. The strongest memory aid is still the simplest. A vented roof needs intake, airway, and exhaust. An unvented roof needs a complete thermal and moisture control assembly. The word unvented never means unmanaged. I made an audio practice quiz for this specific episode, so you can test the ventilation ratios, airspace rules, unvented attic distinctions, and safety decisions you just studied. It is audio-based. The questions are read aloud, and you answer by tapping, because I know you may be studying while driving, working, or moving between jobs. Go to the description below this video. You will see a link that says PassTheCSLB. Tap it. It will take you straight there. Comment below with any questions about the material I covered. Subscribe so I can help you stay on track through every episode until you get your license. I am rooting for you, and I want this study time to feel useful every step of the way.